Good day, everyone. Today, we will explore two important ideas that explains how our planet changes over time: the continental drift theory and the seafloor spreading. Together, these ideas help shape what we now call the theory of plate tectonics. By the end of this video lesson, you should be able to explain Alfred Wegener continental drift theory, identify evidences that supports the theory, describe seafloor spreading and its evidences, and finally, connect these two ideas to understand plate tectonics. Take a look at South America and Africa. Don't they look like puzzle pieces? This observation made scientists curious. One of them, Alfred Wegener. He believed that the continents were once joined together and have drifted apart. Let's see how he explains this. This observation led Alfred Wegener to propose one of the most important theories in earth science: continental drift theory. Wegener, a German meteorologist, proposed the theory in 1912. The continents were once part of a supercontinent called Pangaea. Over millions of years, this supercontinent broke apart and the continents drifted to where they are today. At first, his idea seemed far-fetched, but he had strong evidences to support it. Evidences for continental drift theory: fit of the continents. Wegener's evidence included four major points. As mentioned from the previous slides: fit of the continents, the puzzle-like fit of Africa and South America. The most accurate fit is seen not just on the shorelines, but along the continental shelves, the underwater edges of the continents. This was the first clue that continents might once have been connected and later drifted apart. Fossils of freshwater reptile Mesosaurus were discovered in both South America and Africa, yet Mesosaurus could not have crossed the vast Atlantic Ocean. Fossils of plant Glossopteris were found in Africa, South America, India, and Antarctica, showing that these regions were once shared a similar environment. The presence of identical species across oceans suggests that the continents were once physically connected, allowing species to spread freely. Rock and mountain correlation: similar formations across oceans as evidence of continental drift theory. The Appalachian Mountains in North America match in age, structure, and rock type with the Caledonian Mountains in Scotland and Scandinavia. This indicates that they were once part of the same continuous mountain chains before the Atlantic Ocean formed between them. Rocks and mountain evidence shows that physical geography, not just biology, supports the idea of a supercontinent. Climate evidence for continental drift theory. Glacial deposits, scratches, and till have been found in present-day tropical regions like Africa, India, and South America. Coal beds in Antarctica. Coal deposits, which form from lush tropical plants, were found in Antarctica, which today is a frozen desert. This shows that continents have shifted positions over time. Areas that are now tropical were once near the poles, and Antarctica was once warm enough to support a forest. Despite strong evidences, Wegener could not explain how continents actually move. He suggested forces like Earth's rotation, Moon's gravity, and tides, but scientists of his time found those explanations weak. This is why his theory was initially rejected. However, in the 1950s to 60s, technology allowed scientists to map the ocean floor through echo sounding or sonar, which means sound navigation and ranging. They discovered huge underwater mountains called the mid-ocean ridges. This marks this pattern across the oceanic crust is the location of your mid-ocean ridges. Harry Hess in 1960 proposed seafloor spreading. According to Harry Hess, new crust forms at the ridges and spread outwards. This is seafloor spreading. This explains the mechanism Wegener, Wegener was missing. At mid-ocean ridges, like the Mid-Atlantic Ridge, hot magma rises from the mantle. When this magma cools, it solidifies. It solidifies into new crust, which is mainly basalt. As more magma continues to rise, it pushes the newly formed crust outward from the ridge. This explains why youngest rocks are found always closest to the ridge, while older rocks are located farther away. It provides the mechanism Wegener was missing, showing how continents are carried apart by the movement of the ocean floor itself. Earth has a magnetic field with a north pole and a south pole, like a giant bar of magnet. Normal polarity is when magnetic north points to today's north. Reverse polarity, on the other hand, shows magnetic north points to today's south. This illustration clearly differentiates normal polarity from reverse polarity. Over millions of years, Earth's polarity has flipped back and forth between normal and reverse, as represented by color red, orange, and light orange normal polarity, and the light blue one, the reverse magnetic polarity. As new crust continuously forming at the ridge, these changes are recorded in the rocks as alternating bands. The result is a pattern of magnetic stripes running parallel to the ridge. Crucially, these stripes are symmetrical on both sides of the ridge, showing that the crust is spreading outward equally in both directions. As magma rises at the mid-ocean ridges and cools into basalt, the rich iron minerals inside the rocks line up with the Earth's magnetic field at the time. This means every new strip of oceanic crust acts like a tape recorder, preserving the direction of the Earth's magnetic polarity when it is formed. These symmetrical stripes are some of the strongest evidence for seafloor spreading. They not only prove new crust is forming, but also give scientists a way to measure spreading rates by comparing the width of the stripes with the known ages of the magnetic reversal. And of course, if you might ask what is the polarity today, at present we are under normal magnetic polarity. For emphasis, the evidences for seafloor spreading includes the following: magnetic reversal, rock shows pattern of Earth's polarity switching, age of rocks, younger near the ridges, while older rocks are found farther away from the ridge. Ocean drilling confirms that the oceanic crust or the seafloor is younger than the continental crust. Now the pieces come together. Wegener, Wegener's idea explained that continents move, but does not show how it moves. Harry Hess' discovery of seafloor spreading explained how continents move. When combined, these form the basis of the plate tectonics theory, one of the most important theories in Earth science. We finally come to the last part of today's presentation. What you're going to do is to perform this activity called Future Earth. If continents are still moving today, what will Earth look like 100 millions of years from now? Your output is to creatively produce a sketch map, creative at the same time science-based. And then write a short written explanation, 3 to 5 sentences, on why you think Earth will look this way. And write your output in a short size bond paper. Thank you so much for your time, everyone. And always remember, the earth beneath our feet is not still. It's moving, reshaping, and creating the world we see today. This is King Huan Learnings. Keep going, keep growing, embrace learning.